Hi, this is Brendan Baines, professor of mathematics at Lipscomb University, here to talk to you today about graphing using XY tables. In this app, you're going to learn how to create an XY table and also how to use that table to graph a function. Before we do that, we should talk about what do we mean when we say 2, 4, the ordered pair 2, 4 is a solution to the equation 2x plus y equals 8. This is a big equation. If we had one variable, then our solutions would be single values like x equals 3, x equals 4. But in this case, we have an equation that has two variables, an x variable and a y variable, and so we are going to talk about their solutions as ordered pairs. Okay, so when we let x equal 2, and we let y equal 4, and we substitute those into the equation 2x plus y equals 8, what we see is that we get a true statement. Okay, 2 times 2 is 4, plus 4 would be 8. We look at the ordered pair 2, 8, then we see that that is not going to make a true statement for the equation 2x plus y equals 8. And in that case, we would not say that 2, 8 is a solution. Okay, here's another example. We want to show that the ordered pair 6, 4 is a solution to the equation y equals x squared minus 5x minus 2. So we substitute 6 for x and 4 for y, and we just determine whether we get a true statement or not. And so here we see that when y is 4 and x is 6, and we simplify that expression, we do end up getting 4. So that's a true statement. That allows us to say that 6, 4 is a solution to this equation. Consider the equation y equals x squared minus 5x minus 2 again, but now consider the ordered pair 2, 0. When x is 2 and y is 0, we end up getting the statement that 0 is equal to negative 8. That is not a true statement, and so the ordered pair 2, 0 is not a solution. So now we ask, what are we doing when we graph an equation? We've probably all seen graphs at some point. What are those graphs representing? Well, we're looking at the solutions to the equation. Just like we saw that the ordered pair 2, 4 is a solution to the equation 2x plus y equals 8. We could continue to find ordered pairs that make that equation true. We could do x is 1 and y is 6, x is 0 and y is 8. All of those would work. So we're trying to visually represent where those ordered pairs are that make the equation true, or that is where the solutions to that equation are on the xy plane. We're going to talk about graphing using an XY table, and we will continue to use XY tables throughout the course. XY tables are tedious at times, especially if we don't know what the graph looks like to begin with. Throughout the course, we're going to build our library of functions to where we're going to know what certain functions should graph to be. We're going to know this kind of function should be a line and so on. But at any rate, the idea is we're going to find enough ordered pair solutions so that we can see what the graph looks like. To help with that, it would be good if we know what some of our common functions look like, what their graphs look like. And so you might want to pause now and take a look at the following functions and try graphing those either in a graphing calculator or go to Wolfram Alpha and graph those. These will serve as representative graphs for these types of functions. That is, functions of these types will have the same general shape. Okay, let's make an xy table for the function f of x equals negative 3x plus 1. We'll start by just picking values of x and then finding the corresponding y value that makes a true statement. I've picked negative 2 to 2 for the x values, negative 2 to 2, and I've just picked those. Those are just kind of a standard set of x values to start with, as long as those x values are in the domain of your function. You might choose a different set of x values to plug in, and that would be fine, as long as we plug in enough ordered pairs so that we know what the graph looks like. When we plug in negative 2 into the equation, again, that's just like doing f of negative 2. We see that we get negative 3 times negative 2 plus 1, which is 6 plus 1, which is 7. And we continue to do that for each of the other x values. This creates a set of ordered pairs that we can then plot on the xy plane. And you can see the look of the graph there once we connect those ordered pairs that we plotted. And this graph turns out to be a line. Let's take a look at a second example. We're looking at f of x equals x minus 3 to the 1/2 power. The 1/2 power is also the same thing as a square root. So when we're thinking about this, we really are talking about the square root of x minus 3. To make our xy table, we need to pick values of x and find the y that corresponds to that value of x. That creates a solution to the equation. If we try x equals 0, then we're going to see that we get the square root of negative 3. The square root of negative 3 doesn't exist, and so we cannot use the x value 0 because there are no y values paired with it. We would say that 0 is not in the domain of f of x. You might pause and think, are there other values that are not in the domain of this function? Let's check x equals 1. If we do f of 1, we get the square root of 1 minus 3, which is the square root of negative 2. This is also not a real number, so we can't use x equals 1 either. So what numbers can we use? Well, when we can only take the square root of 0 and numbers greater than 0. Since this function's equation has us take the square root of x minus 3, it's going to stand that we must use x values that maintain that x minus 3 is greater than or equal to 0. And so that means that we can only use x values that are 3 and greater. So here's the xy table that I created. Again, the choice of x values, other than being limited by the domain, I've just picked x values that I knew would have nice square roots when plugged in. These are not the only x values that you could choose. They're just a subset of x values that we might look at in our xy table. Once I get my ordered pairs in my xy table, I plot those in the xy plane and connect those, and we see the look of the graph. This example is important because there are certain functions for which we can't use just any x value that we wish, and so this is a good representative of that idea. A lot of our functions that we talk about in this course will be nice in that they are not limited in their domains. That is, their domain is all real numbers. There are other times that we might consider x values that can't be in the domain. One example would be f of x equals 1 over x. If x equals 0, then that's going to have us divide by 0. 1 divided by 0 is undefined. Also, in applied scenarios, we usually do not use negative numbers for things like length, because we can't have a negative length. And so in those applied scenarios, we limit the domain for applied reasons.